Welcome to Brain Vision.
A certain brand of freezer is advertised to use 730 kilowatts hours of energy per year. Assuming the freezer operates 5 hours a day, how much power does it require while operating? If the freezer keeps its interior at -5 in a 20-degree C room, what's the theoretical maximum performance coefficient? What's the theoretical maximum amount of ice that the freezer can make in an hour starting with 20 degrees C? Okay, so first part, I wrote down all of the givens ahead of time. And so first we want to get the power required while operating, assuming it operates for 5 hours a day. So power equals question mark. So power in general is energy over time. So let's see, this is going to be part A. And the energy is given by this first quantity, 730 kilowatt times hour, kilowatt hours. And the time is this T run. So I'll go ahead and put that coefficient on the T just to make it clear. So T run, and that's 1825 hours. So if you take the ratio of 730 kilowatts times hours divided by 1825 hour, then you should get that the power is 400 watts, so 400 joules per second. And for part B, the goal is to get K. So K is equal to TC over TH minus TC. I forgot to write down the temperatures in the givens, but that's okay. I can just write them down here. So T cold is -5 degrees C, but of course you can't forget to use Kelvin. And then T hot minus T cold, that's just our delta T. So that's just this minus, oh, never mind, that's not our delta T. This T hot minus T cold is the difference between the two reservoirs. That delta T I'll talk about later in the problem. So this delta T is this T hot, which is 20 minus -5. And so if you plug that into a calculator, notice I didn't convert the numerator to Kelvins, and that's because temperature differences are can be equivalently done in Kelvins versus Celsius. So if you put that into a calculator, maybe you'll get what I got, which is 10.7. And now that I remember it, I will box that. Okay, all boxed up. So for part C, now we want to get to like maybe a more question you could actually picture asking. So what is, how much ice can this freezer make? So for this, we kind of need 3 equations. I kind of thought about it ahead of time and organized it this way. One, we need to figure out how much heat is required to make ice. So we want to use, so we have water, and we first need to cool it to 0 degrees C, where and that's the temperature that ice is formed. So to do that, you get MC water delta T. Okay, and then we need to cool it. We need to, now that we have water at 0 degrees C, we need to continue to pull out energy from the system, and to figure out the amount of energy, you just need to figure out the heat associated with the phase transition, which is just L. And so both of these terms should be negative. This delta T is already negative, so it's only minus 20K because it doesn't have to go all the way to -5 to freeze. It just goes to go to 0. And so, yeah, so I think everything's kind of written out, and we have our LF, but we don't have QC, so we need QC. So that brings me to equation 2. This is relevant for all refrigerators. So QC is work times K. All right, do we have those ingredients? Well, we have K, we found it in part B, but we don't have W. W, though, we can get from part A because we have the power, and power is energy divided by time, and specifically it can be the energy due to work divided by time. So from that, you can get work is equal to power times time. And now we just want the time. So they're concerned about making this in an hour. So we want to just we want to get how much time is in an hour, and these are all in SI units. So I converted 1 hour into seconds. And then I might as well just talk a little bit about T run. I kind of forgot to talk about this. So just a quick little tangent to get the time running. It was assumed that it was run for 365 days per year and 5 hours per day. So that's how I got T run. Whoops. And that was all, of course, for part A. So yeah, so you just need to multiply to get back to part 3 of part C. You just need to get the time that the time that you want to make the ice by. So that's 1 hour, 3,600 seconds times the power, which is 400 watts. Okay, and then you if you plug that in there, you got QC is PT ice times K. And then if you plug this in here and you algebraically manipulate it, you get mass is equal to PT ice K divided by C. Oh no, I can't write down here. Okay, let's C delta T minus LF. And that's just C of the water. Anyway, if you take this and plug it into a calculator, then you will get hopefully get 36.9 kilograms.